Alright, so today we're going to evaluate limits algebraically using substitution and some manipulation. And before we get started, I just want to take a little bit of stock of what we've sort of been able to do with the limits. We've been able to figure out limits and evaluate limits both one-sided and two-sided by making a table of values. And also, if given a graph, we can evaluate limits fairly easily as well. Now, what I want us to do is sort of consider the situation in which neither of these options is going to be advantageous to us. In the first, creating a table, first you have to have the function, right? You have to know what the function is. But it's a little time consuming, right? You've got to go into your calculator, you've got to type in the function, you've got to evaluate it, all these different points. And that can be a little cumbersome and maybe not so efficient. Similarly, with a graph, if we don't have a calculator, graphing the function could be also very time consuming. And so we want to develop a way or multiple ways of figuring out the limit of certain functions as they approach certain values without having to do either of those, just by kind of looking at the algebraic representation of the function. And so that's what we're going to focus on today. Alright, so go ahead and use methods that we've previously gone over and learned to answer these three questions. Alright, so first off, we're going to evaluate the two-sided limit of f of x as x approaches 3. So with the graph, what we have to do is just sort of look at, as we get closer and closer to 3 from the left and get closer and closer to 3 from the right, does the limit as we approach from the left and the limit as we approach from the right, are those equal? And so as we approach from the left, we see that the function approaches a value of 10, and as we approach from the right, we see that the function approaches a value of 10. And so the limit as x approaches 3 of f of x is equal to 10. Okay? And then we also want to know, what is the value of the function at an x value of 3? And this is pretty easy as well. We just see, well, when you plug in 3, the value of the function is also 10. So what do we notice here? Well, we notice that the limit and the value of the function are the same. They're equal. Now, we saw in a previous example that that's not always the case, right? We saw a situation where there was an open point and then a closed point somewhere else. And so the limit was approaching something, we know what the limit was, but the value of the function was actually different. And so what made it possible, what made it the case that the limit and the function had the same value? And what you might notice is that the function is smooth or continuous, right? There's no bouncing around of the function. And this is an example of a continuous function. And so what we're going to find is when the function is continuous, it's actually the case that the limit as we approach some value and the value of the function are actually the same. And so for our purposes, we're going to define what a continuous function is soon. But for our purposes, let's just kind of characterize why this function is continuous. It's continuous because we can draw the graph of this function without lifting our pencil off of the paper, right? So you could imagine if there was an open point there and it was then defined down here, we would have to lift our pencil or pen off of the graph in order to then continue drawing the function, okay? So we're going to use this now to our advantage. When we have a continuous function, it's going to be really easy for us to figure out the limit. In fact, this is a fact, or a theorem, as we call it, and a theorem is something that has been proven to be true, and so we can take advantage of it at all times. It's proven to be true for all values. So here it is. If a function, f of x, is continuous at some value a, then the limit as x approaches that value a of f of x is just the value of the function at that value a. And I've drawn a sketch of a graph to help us understand what this means. So a continuous function, f of x is continuous, meaning I can draw it without taking my pencil off the paper. Right? It's a nice smooth curve here. And if the function is continuous at some value a, and it certainly is, right? So at this value a here, I can draw the function around this value a without taking my pencil off of the paper. Then the limit as we approach a, so we can approach it from the left or from the right, is just the value of the function when we plug in a, right? So the limit is actually the value of this point here, and what is the value of this point here? Well, it's whatever we get when we plug a into the function, in other words, f of a, okay? And so this will allow us to just plug in the value instead of doing, making a table or actually having to draw the graph. So let's take a look at an example and see how we can utilize this fact to our advantage. Okay, so let's try and evaluate this limit. And this looks a little scary at first, right? There's kind of a lot going on. But what I want you to do is try and utilize this theorem here and see if you can make sense of this situation and figure out what the limit is. And then once you've tried it, we'll go ahead and we'll take a look at the answer. All right, so if we want to take advantage of this, right, we need this function, f of x here, we need this to be continuous at the value that we're trying to approach, right? We need it to be a nice, smooth, easy to draw curve when we're approaching -2. And so our first task is to just identify what type of a function this is and see if it's going to be continuous. And because we've looked at many rational functions, this is a rational function, we know, look, a rational function is only going to be undefined. In other words, it's only going to be unable for us to actually draw the function in a nice smooth curve when the denominator is 0. So as long as this value doesn't make the denominator 0, we should be in really good shape. And that's a general rule. I want you to kind of make note of that, sort of store that in your memory bank, right? To test whether or not this function, or in most cases, any function is going to be continuous at a certain point. You want to kind of plug it in, and if you don't get a denominator of 0, then you are in good shape, okay? So we've checked the only value that makes the denominator 0 is 2, and since we're plugging in -2, we aren't going to have that issue. So we can take advantage of our theorem, and our theorem says, look, if it's continuous at this value a, then the limit as you're approaching that value a is just going to be equal to the value of the function when you plug in that value a. And so all we have to do to find this limit is actually plug in, or in other words, substitute in this -2 into our function. And so to do that, we'll just plug it in, and we have -2 squared, which is 4. 8 times -2 is -16 minus 20, divided by -2 minus 2, which is -4. And if we add up the numerator, we get -32, and -32 divided by -4 is going to be a +8. So the limit as x approaches -2, the two-sided limit is in fact 8. Okay? And if you want to test this out, I encourage you to. What you should do is graph this function and take a look at it. Zoom in on when you're close to an x value of -2, and you'll notice that you have a nice smooth curve, and as you approach from the left and as you approach from the right, just like we've shown here, it's going to be getting closer and closer to the value of 8, which is also the actual value of the function at -2. Okay, so we can take advantage of that. It's really easy. Whenever you can actually substitute in, you should do so quickly, get the answer correct, and move on. All right, here's one more for you to try. Make sure that you can use the theorem before you use it. If you can't, you don't want to make that mistake. So go ahead and give this one a try. All right, so in order to determine whether you can use substitution, we need to make sure that this is defined. This is a rational function. So again, it's only going to be undefined when the denominator is 0. And if you were to look at this and you thought, how could I figure out what will make this 0? You could set it equal to 0 and solve. So if you were to set x squared plus 4x equal to 0, you could solve by factoring. By factoring out an x, you get two linear factors, x times x plus 4. And you'd see, look, it's only going to be equal to 0 when x is either 0 or -4. But that's a lot of work. So really what you want to do is think, this is where I'm trying to evaluate it at. I have a rational function, and I know that rational functions are always continuous so long as the denominator is not 0. Does this make the denominator 0? And that's a lot easier of a process than actually setting this equal to 0 and solving. If you plug in 1, you don't get 0 in the denominator, so just go ahead and do that and evaluate your limit. And if you do so, you're going to end up getting a value of 3. All right, let's take a look at one more. Why don't you take a second and see if you can decide whether or not we can utilize the continuity of this function to find the limit. What you notice is we can't. This function is undefined at x equals 2. Does that mean we can't find the limit? No, right? We want to know what's happening as we approach 2, and so just because it's undefined at 2 doesn't mean the limit doesn't exist. It just means that we can't plug in 2 and actually find what the limit is, right? It's going to be undefined there. So let's rewrite this statement, and this is something that it's a key point that you want to remember is if I'm going to simplify this function here and rewrite this statement, I can't leave out the limit piece, okay? Because this statement is saying take the limit as x approaches 2 of this function, and so this is equal to another statement where we're saying the limit as x approaches 2, right, of this function. So we have to keep the limit statement there. And let's factor this, and so the numerator is going to have 2 linear factors, and if we go through quickly and think about what will multiply to be negative 20 and add to be 8, and so we can think about positive 20 and negative 1, no, positive 10 and negative 2, and yes, that works. So we have x plus 10 and x minus 2 divided by x minus 2. And so now notice that we have these 2 common factors, and what usually we have to be really careful when we cancel these out, because we have to say, look, we can cancel these out, they're equal to 1, right? X minus 2 over x minus 2 is equal to 1 everywhere, but not at 2. But that's okay, because we're looking for the limit as x approaches 2. So when we're getting close to 2, from the left or from the right, well, x minus 2 over x minus 2, when x is getting closer to 2, is always going to be 1, right? It's only when x is actually equal to 2 that that's a problem. So we can cancel these out just fine, and we'll still be able to evaluate our limit. So now we can rewrite this again as the limit when x approaches 2 of x plus 10, right? Because these two are always going to be 1 as we're approaching 2. And now we have a function that's continuous, right? So we can just go ahead and plug in. Now we can use substitution. We plug in 2 here, and so this is going to be equal to whatever this function is when 2 is plugged in. So it's 2 plus 10 or 12. Okay? And so I want us to really visualize this. And so to do that, we're going to actually graph this function. And so if you were to simplify this function, you'd say, look, it's x plus 10 as long as x is not equal to 2, right? So this function here, f of x, is equal to x plus 10 when x is not equal to 2. So let's go ahead and sketch that graph really quick. Alright, so there's my attempt at sketching the graph here. And the reason this is the case is, look, this is a straight line because x minus 2 over x minus 2 is always 1, except when you get to 2, well, then the function is just undefined. So you can't define it there. It's open, but it's a straight line everywhere else. And so you can clearly see that as we get closer and closer to 2 from the left and from the right, we're approaching the same value, which is 12. Okay? So when we can't use continuity, we should always look to simplify our function by factoring and canceling. All right, let's take a look at a couple more. These are slightly more complicated in the way that they start out, and so I just want to bring up a couple of sort of tricks that you already know but might have forgotten. So try these on your own first, and then we'll talk through them. Okay, so looking at the first one, we immediately notice that continuity is not going to work in our favor. It's discontinuous. And I want to go through the thought process again. So it's discontinuous because the denominator is 0. We're going to see this over and over again. So we need to manipulate the function so the denominator isn't 0, which means we need to cancel this factor that is the trouble factor. And so we immediately look to get an x plus 3 in the numerator. But this numerator is a little different. We can't just factor this. We've got a rational expression here. And so to get rid of this divisor so that we don't have a divisor of x plus 4 anymore, if we want to get rid of any divisor in any denominator, we just multiply by the denominator. So we're going to multiply this whole thing by x plus 4. And of course, we realize that if we multiply the numerator by x plus 4, we must also multiply the denominator by x plus 4. Okay. And notice that I'm doing this within the limit, right? So when I rewrite this expression, I'm going to have to include my limit statement to make sure that I'm staying true to what I'm evaluating. So here in the numerator, when we multiply, and you also want to remember that this is what we're multiplying, so we're distributing. So we're multiplying x plus 4 by this, and that's great because x plus 4 over x plus 4 is going to be 1. And so let me write my limit statement before I forget. Okay, and so in my numerator, I have x, and then plus 3 times this, and so I distribute plus 3x plus 12. Okay, and in my denominator, now be careful, I could FOIL this, right? I could multiply this, but I'm trying to get rid of this factor. So we want to leave it as x plus 3 times x plus 4 so that we can hopefully factor the numerator. So now we're in good shape. We just need to somehow factor the numerator, and we can do this. So we can gather together these like terms here. Right? This is going to be 4x. And we can factor the numerator now. Limit as x approaches -3, and we can factor out a 4, and so we'll have 4 times x plus 3. And just a kind of a heads up, if you're going to be able to evaluate this limit, you're going to have to be able to cancel the denominator. So have faith and keep moving, right, knowing that something is going to show up. You're going to be able to factor this numerator eventually over x plus 3 times x plus 4. Okay? And these will cancel, so you can now rewrite as, again, the limit as x approaches -3 of 4 over x plus 4. And now you can take advantage of the continuity. This is continuous, right, when you plug in -3, and so now we can plug it in and evaluate our function, or sorry, our limit. It's going to be 4 over -3 plus 4, which is going to be 4 over 1, or 4. Okay? So a little trick there. All right, let's take a look at the second one. So here again, plugging in 25, both my numerator and my denominator are going to go to 0. And obviously that's not good at all. So again, same idea, right? If I'm going to be able to evaluate this limit, then I'm going to have to be able to get rid of the denominator that goes to 0. That just is going to have to happen. And here I can use a little bit of a trick. And this trick, and you might want to remember it for future reference, is called multiplying by the conjugate. Okay? So anytime you have a square root of something in the denominator, you'd like to sort of get rid of it. And so to get rid of this, you're going to multiply it by the conjugate. And the conjugate is where you have the same first term, the same last term, but you switch the sign. And I'll show you why this works. So we're going to multiply by the conjugate, which is the square root of x plus 5. And you're going to have to multiply the numerator by that as well, the square root of x plus 5. And here's why this works. Okay? When we FOIL the denominator, we're going to have x, square root of x times square root of x, which is x, okay? But then notice, we're going to multiply negative 5 by square root of x, and we're going to multiply positive 5 by square root of x, and those are going to then cancel. You'll have negative 5 square root of x plus 5 square root of x. That's 0. So you get rid of the square root, and that's why we do this. Okay, so you might want to commit to memory that the conjugate, multiplying by the conjugate, will get rid of the square root there. So I can rewrite this expression, the limit as x approaches 25. And let's just handle the denominator first. So as we found out, we're going to have x minus 25. And now I need to be very careful because look at what I'm doing. I am now plugging in 25, and so the denominator will still be 0. Okay? So notice, again, I go through my progression, my thought, and I go, okay, I need to cancel out x minus 25. So I need a factor of x minus 25. Now look at your numerator here. You're going to have this times this, okay? And just take a look for a second and notice, do you have anything that is close to x minus 25? Well, this has a square root in it, so that's not going to help you get anywhere, right? This doesn't. And notice that you have x and you have minus 50, right? 2x minus 50. And this is very close. It's just that you've got a 2 and a 50. Well, if you factor out the 2, then you're going to end up with x minus 25. So let's just do that. Let's factor out the 2. We'll have 2 times x minus 25, still multiplied by this other factor here, square root of x plus 5. And now you're in good shape because you can cancel out this troublesome factor, okay? And it's okay to cancel out again because I'm approaching 25. It doesn't matter that it's discontinuous at 25. And so now the limit as x approaches 25 of 2 times the square root of x plus 5. And notice now, when I plug in 25, I don't have a discontinuity. It's continuous now, so I can plug in 25 and evaluate. So this limit will just be whatever the value is when I plug in 25 to this function. So it's going to be 2 times the square root of 25 plus 5. And inside my parentheses, I have 5 plus 5, which is 10, times 2, which is going to be equal to 20. Okay? So those are a couple of tricks in evaluating kind of some complicated looking rational functions. I encourage you to make note of them. They will come in handy, and you can use them in many different situations. All right, so now I'm just going to give you a couple of problems to practice on your own, make sure that you can apply some of these strategies, and we will go over and practice a little more in class.